Okay, hi folks, continuing along, we are going to solve or make our best attempt to solve the radial component of the hydrogen atom Schrödinger equation. So let's get there and do it. And as we're going to find out, this Schrödinger equation can only be solved for various boundary cases. And the math for this, like in our kind of previous sections, gets so complex that I don't really find it worth our time to go through the full solutions. Instead, we're going to talk about how the solutions are arrived at and what their properties are. So this is a slight algebraic rearrangement of the equation that we came up with last time for the radial component. And recall u of r is this function r times r of r. And in this function, you'll notice this is very much taking on the spirit of the Schrödinger equation. So we have our kinetic term, the negative h bar squared over 2 mu times second derivative in r. This entire chunk right here is what we call our VEFF. That is our effective potential energy. And you will notice now that there are two terms in this effective potential. There's the Coulomb's term, and then there's the angular momentum terms. So we're going to have this competition between Coulomb's law, so the charges, and the angular momentum. And then, of course, all of that equals E times u of r. So our solution for E here will be a solution in the radial component, which we can then combine with the angular component to get the total solution. So the three scenarios we're going to look at are when L is 0 or when L is non-zero, when the electron is very close to the nucleus, or when the electron is very far from the nucleus. And so those will give us approximate solutions which work very well. So let's look at our first condition, and I'm going to combine two of those that we just discussed, when L is equal to 0 and when R is equal to 0. So first of all, we should note when L is equal to 0, we can see that this is entirely Coulombic. So that means there is no angular momentum on the z-axis, and the force of the proton on the electron in that z-axis is purely Coulombic and attractive. So that allows us to make a couple of simplifications. So for one, we can cast out this term because we're saying that L is equal to 0. And similarly, when we're saying that R is practically equal to 0, we will impose the following for this function. U of r is r times r, and we'll say that that is roughly equal to 0 because of the r that's right there. So that means we will also throw out this chunk right here. And what we're left with is the approximate equation, so which is going to go as the following: dr squared u of r. So we can't cast out that term because it's the derivative. And then now I'm going to apply all of those constants through, and noting that the collection of all of those constants was 2 over the Bohr radius. We can write that simply as such. And all of that approximately equals 0. So the solution for this we could do quite easily. And as it turns out, an approximate solution for this is a polynomial. So u of r, to solve this, so right, we would go through our ansatz method, and we would get the following. U is a polynomial that is going to take on that form where we're going to have, a times r squared plus b of r plus c, etc. We could imagine there being a cubic term and so forth. This is all that I'm going to describe for this, that it's just this approximately a polynomial for this condition. We're going to move on to the next conditions and get an approximate solution. So now, category 2, when L is non-zero and R is still close to the nucleus. So now we have this case going on right here. And what we want to think about when L is non-zero, the electron has orbital angular momentum in the z-axis, and it is being flung away from the nucleus, right? Imagine that famous carnival ride where you're spinning around and you get thrown against the wall and they drop the floor out, super fun and scary. So this is what's happening to our electron. It's being flung away from the nucleus. When R is very close, there's competition between the electron being flung away to its angular momentum and the Coulombic force attracting it. So when it's very, very close, the angular momentum is strong enough to dominate the attractive force, and the electron is flung away from the nucleus. And you can see when the radius is very far out, which we're going to do in the next one, these two different potentials become roughly equal to each other. But you can see now in this case, when R is very close, the effective potential is dominated by the angular momentum. So now that means we can cast out this term in this solution, and we're still going to cast out this term, because if we're saying that R is practically zero, we'll say this whole thing is approximately zero. So now we get the following, and again, this is just an approximate solution where I've pushed all of the constants through. And so now we can say that's plus L times L plus 1 over R squared. So all of those constants went away when I pushed these other constants through. Times U of R, and that all approximately equals 0. And what we get for this solution, so solve this sucker, we get that U of R is approximately equal to A, some normalization constant, times R raised to the L power. So it's not immediately obvious how we'd get to this solution. So that's why we're just going through this rather quickly. Okay? So this is what our approximate solution looks like under this condition. And then finally, under our last condition, we can look at when R tends very far away from the nucleus, either from, and we can think of both cases when their L is 0 and when L is non-zero. And as it turns out, when we look at this, these two potentials, you can see both of them are becoming approximately equal, and they're also both becoming negligible. So when R is very far from the nucleus, both angular momentum and Coulomb terms can be ignored. Those forces are both very weak at large distances. So that means we're just going to cast out all of our potential energy terms. And we're going to end up with the following. So that's going to be d dr squared of U of R. And there ends up being an asymptotic relationship to this because of the way this potential energy is approaching 0, but never quite will make it to 0. And so let me rewrite that again so that it's obvious how that asymptote is applied. So that's going to be plus 2 mu E over h bar squared U of R, and that is asymptotically equal to 0. So in other words, we've set our potential energy term equal to 0. And now when we go to solve this thing, hopefully we can see that we've already solved this sucker. So we're going to get U of R is asymptotically equal to E raised to the negative K times R. And so for reasons that aren't necessarily immediately obvious, but hopefully will become as we think about this, we're only looking at that negative solution because of the angular momentum considerations when the electron is close. Additionally, hopefully what we recognize, that K solution, right, is the square root of 2 mu E over h bar squared. It's our wave number solution. And we're also going to impose that this must be the absolute value of E. And the reason why we're doing that is because we have this other boundary condition that we're going to create, which says E must be negative for all bound states. And we can see that here in the effective potential energy operator, that these potentials are negative. So this is where we don't worry so much about the imaginary solutions because we're going to impose that E must be negative for all bound states, and thus we can use the absolute value. So what happens when we combine all of these things? Well, we get the following. We know that when when the electron is close and has angular momentum, this r raised to the L power will dominate. We have this polynomial in R that actually bridges the two ends of the function. So that's in the case when our potential energy and our angular momentum is in competition with each other. And then finally, we have this exponential in R, which is dominant when the electron is far from the nucleus. So, of course, then we get a normalization constant. We have this R raised to the L power term. We have this polynomial term, and we have this decaying exponential. And so now we notice here we've collected a whole bunch of constants. So we're going to call rho 2zr over NA. And yes, we get the reemergence of quantum number n. So that is still our principal quantum number, which came from solving the particle in a box model, right? So this previous solution effectively becomes a particle in the box model. We have the collection of constants describing the Bohr radius. And then what we can see here is we're imposing already that this function is normalized and equal to 1. So this normalization constant is buried within the solution. And 2, we also see the emergence of this new set of polynomials known as the Laguerre polynomials. And they are the bridge that connects solutions when R is very close and when R is very far. And it also creates another bridge between quantum numbers n and L. So we get that L can take on all integer values up through n minus 1, where n is still the same solution that we got before from the particle in a box model. And so now when we connect all of these, we get this huge table of radial components, just like we saw with the spherical harmonics, where now, based on our set of quantum numbers, we get a particular radial component. Okay, so that was a lot. So we're going to explore the properties of these radial solutions in the next video.